Hi, so this lesson, 5.4, is going to talk about the sum and difference identity formulas for trig. Let's see, I'm trying to think if you saw these in Honors Algebra 2, maybe not, but those of us who took trig did see a little bit of these. And back in the day, we had to do a lot of these identity swaps because they had to look up trig function values in a chart. So you wanted to make sure that you were using the basic trig ratios and trig functions that were occurring on the unit circle as much as possible. So now we have technology that will evaluate like the tangent of 65 degrees. But, you know, before that moment, we had to do a lot of thinking. So what we're going to do today is talk about these different identities, how we can trade them out, why they're useful, and really it's just a game of algebraic manipulation with a little twist of trig functions thrown in there. So if you have what we call the sum identities, and they use different Greek letters alpha and beta here in these identities. Cosine of alpha plus beta is cosine alpha cosine beta minus sine alpha and sine beta. It's quite a mouthful there. And these are on your formula sheet. So you, and I think ours is pink, not blue. You don't have to have these memorized for the sum or the difference identities. I remember memorizing these. And it wasn't super fun, but it's one of those things where like you might accidentally end up memorizing them. So whatever works for you, it depends on how much practice you get with them. We are going to be using the identity formula sheet though. This example is already done for you. So it has the sine of 15 degrees, which if we have a graphing calculator or a calculator that does trig functions, doesn't even have to be a graphing one, we could have just typed in sine of 15 degrees in degree mode and got a truncated decimal answer that's appropriate and equivalent to that answer. Now this is what we call the exact answer. And the way we find it is we break up that problem instead of 15 degrees, because that's not on my unit circle. What if we rewrote that as 45 minus 30 degrees? Then we could use the difference formula where it says sine alpha times cosine beta minus sine beta times cosine alpha. Blah. Sine, cosine, cosine, sine. If we look at the values from the unit circle, we just simply substitute them all in, one at a time. And then we kind of have this mess of rationalization going on. So square root of 2 times square root of 3 is square root of 6 over 4 for this first fraction. And then square root of 2 over 4 is this next fraction here. And then if I try to subtract these, they already have common denominators, so you could rewrite it as square root of 6 over minus square root of 2 all over 4. That is your exact answer. What a hot mess, right? And if we wanted the decimal equivalent to that, we'd have to type it in at that point. So sometimes kids learn these identities and they're like, why do I even need to know these? It's just a game of algebraic manipulation. So recognizing which pattern you're looking at is going to be one of our major tasks. This question is already done for you on the notes. The original problem was cosine of 375, and the way they chose to break that up is 330 plus 45 degrees. You just have to make sure that you're using angle measurements that are off of your unit circle. So, you know, anything in the 30, 45, and 60s family. So that's how they ended up breaking that apart. I'm going to skip that because it's already done for you. But let's take a look at this one. Cosine of negative 15, there's a couple different ways we could set that up. The first one that pops into my mind is instead of negative 15, what if I called this like 30 degrees minus 45 degrees? And then I tried to evaluate cosine of that angle. Well, using the difference formula, which is cosine, cosine, sine, sine, with the opposite sign in between. So cosine, cosine, plus sine, sine. I have this weird memory of Mr. Dredge, one of our teachers, making us recite this over and over and over again. Anywho, to our unit circle, cosine of 30 degrees is the square root of 3 over 2. And then cosine of 45 is square root of 2 over 2. Sine of 30 degrees is 1/2 sine of 45, square root of 2 over 2. And then if I try to clean this up a little bit, this is the square root of 6 over 4 plus square root of 2 over 4. And those are common denominator expressions, so we have square root of 6 plus square root of 2, which does not simplify, all of it over a common 4. Blah! So if we typed that in our calculator, we'd get a really lovely decimal answer, which would have been the same answer had I typed cosine of negative 15. But exact value, so we got to use these trades. All right, tangent of 15. Now, 15 always messes with me because there's so many different ways that we can come up with 15. I'm thinking 60 minus 45. And the reason I'm going with this, instead of like 45 minus 30, is I think about the tangent value at 60 degrees versus 30 degrees. So tangent at 30 degrees would be 1/2, because that's the sine, times the reciprocal of the cosine. And see how there's some weird rationalization effect? As opposed to the tangent of 60, which is the square root of 3 over 2 times 2 over 1. So I would much prefer to do some manipulation with square root of 3 over 1 as opposed to square 1 over square root of 3, because that's going to involve a lot of rationalization that I really don't want to think about. So if at all possible, I don't want to use tangent of 30 if I have to ever. So using my difference formula for tangent, which I'm just reading straight off my page, is tangent of alpha, so tangent of 60 minus, I don't have this one memorized, so I gotta look back and check, tangent of 45 over 1 plus, and then the two tangents multiplied together, tangent of 60 times tangent of 45. Now tangent of 45 is awesome, right? And we just decided tangent of 60 was the square root of 3, so this becomes the square root of 3, tangent of 45 is a 1, and then here, tangent of 60 again is square root of 3, tangent of 45 is 1. So what do we have here? Let's check it out. We have square root of 3 minus 1 over 1 plus square root of 3. Now, I know too, like an algebra student, they have no problems with leaving our answer like that, but pre-calc students recognize that it's not really proper form to have 1 plus square root of 3 in our denominator. So we have to rationalize by multiplying by the conjugate expression to 1 plus square root of 3, which is 1 minus square root of 3. Blah. I don't know why I love this stuff so much normally. I like algebraic manipulation. It really doesn't have a use other than doing more algebraic manipulation and solving an easier question. So if you like this, good news, you have a lot of calc manipulation in your future that you get to use this on. Alright, foiling this together, you get the square root of 3, gross, minus square root of 3 times square root of 3 is 3, and then negative 1, and then plus square root of 3, right? Yeah. Ew. Alright, so my denominator, conjugates multiply together are lovely, right? 1 minus 3. So what we end up with is negative 4 plus 2 square roots of 3 in the numerator over negative 2, which that's gross. So let's divide everything here by a negative 2, and you get a positive 2 minus 1 square roots of 3 over 1. Blah, 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 blah. Alright, that was kind of gross. I apologize. Alright, originally I didn't catch that I didn't want to do tangent of 30, and I had like a rationalization within a fraction, and it was like really awful. Like terrible, in fact. Alright, so none of you like radians, and me neither. So the first thing I'm going to do is I'm going to convert this to degrees by hitting it by 180 over pi, the conversion factor. And that comes out to, what does it come out to? 165 degrees. So frankly, I don't want to think about radians anymore in this question. Degrees I'm okay with. I'm going to change 165 to 100 and, let's do 120 and 120 and 45 added together. That's the same thing, right, as 165? So what if I did the cosine sum formula? So that would be cosine, cosine, sine, sine with the opposite sign. So cosine of 120, cosine 45 with a minus sign, and then sine of 120, sine of 45. Alright, let's start thinking. Cosine of 120, I already did this, so I'm just going to cheat. That's a negative 1/2. Alright. Times cosine of 45, I got that. That's square root of 2 over 2. Minus sine at 120 is square root of 3, positive square root of 3 over 2. Sine of 45 is square root of 2 over 2. So, if I do some simplification here, I have negative square root of 2 over 4 minus, this is the square root of 6 over 4. And then I don't really care about having lead terms as negative here, because either way it's got a negative. So I'm okay with this answer. You're You could factor out a negative or put the negative in the denominator and make these positive, but whatever. I'm good with that answer. All right, so same thing here. 7 pi over 12, no idea what that is. So 180 over pi, this is really the cosine of negative 105. So figuring out how I could possibly break that up. What if I did 100 and... How about 30 minus 135? That would work, right? So this is cosine difference formula again. So it's going to be the cosine, sine with a plus sign in between. So cosine, plus sine. Alright, one at a time here. Cosine of 30 is the square root of 3 over 2. Cosine of 135 is the negative square root of 2 over 2. And then adding to that sine of 30, which is 1/2. And sine of 135 is positive square root of 2 over 2. The second quadrant there. Alright, so this becomes negative square root of 6 over 4 plus the square root of 2 over 4, which I don't mind if you write the answer as negative 6 plus square root of 2, but you could reverse the order so the lead term isn't negative if it bothers you. Square root of 2 minus square root of 6 over 4 is another good answer, but, you know, whatever. Not picky about that. Alright, rewriting is a single trig expression. I prefer these. I don't know, I think it's easier to figure out how to collapse it back down into a single expression. So the first thing I recognize is cosine, sine. Sine is one of the cosine sum and difference formulas. And for cosine, it's always the opposite sign. So this is going to be cosine of alpha minus beta. If I can figure out who they are, you don't have to think too hard, guys. This is your alpha and this is your beta. So this is the cosine of, 7 pi over 8 minus 5 pi over 24. But then, you know, that's not a good enough answer, right? So we're going to have to get common denominators. I'm going to hit this guy by a 3. This is 21 over 24. So 21 pi minus 5 pi is 16 pi over 24, which then reduces. So this is, 2 pi over 3. That's so gross. All right, cosine of 2 pi over 3. Woo! I hope that was the right answer. It's not even on your notes. Fingers crossed and all that. All right, so this one is on your notes. I think. Maybe, maybe not. No, it's not. Let's find one that's on your notes. That guy's on your notes. All right, so sine, cosine, sine. That is an expansion of the sine sum formula because sine keeps the same sign in the middle, alpha plus beta. So if you could just figure out that he's your A and he's your B, or alpha and beta, you're good to go. So this is sine of 20 plus 10. Better, a little ahead of myself there. 20 plus 10, better known as sine 30. But we know what the sine of 30 is, don't we? Sine of 30 is 1/2. So this is the collapsing of it down to a single trig function, and this is me actually evaluating it, which sometimes we can do. Alright, so here, it's one of the tangents. I can tell from there that it's a tangent. I gotta get rid of this thing though, so I can see the rest. Alright, so tangent plus tangent, that is the sum tangent formula. So this is going to be my alpha, this is going to be my beta. So it's the tangent of alpha plus beta, if the formula starts off with tan plus tan. So for us, that'd be pi over 9 plus 5 pi over 36. And if I were to get common denominators, I'd have to hit this guy by 4 over 4. So this is 4 pi over 36 plus 5 pi over 36, which is 9 pi over 36, which is pi over 4, 400 years later. So what we're really evaluating is the tangent at pi over 4, which that's like my favorite tangent. That's a 1. Goodness, that is a good time. Alright, so here we're simplifying, collapsing it back down into the singular expression. Cosine, sine is an expansion of the cosine sum formula. So here's my alpha, here's my beta. Or A and B if you don't like the Greek letter. I'm writing American letters here, or English letters. I'm over the Greek letters today. Alright, so alpha plus beta would be cosine at 90, which we know is a 0. Lovely. Ew. Alright, sine, cosine, sine. That's an expansion of the difference of sine. So this is the same as sine of alpha minus beta, or a minus b. Here's your a, here's your b. I'm just going to write it as, oh, this is kind of gross. So it's pi over 12 minus y, and if they want me to write it as a singular expression, like, there you go, it's done. All right, so this next section is kind of fun. You're verifying those cofunction identities that said the sine of your complement equals the cosine of the other angle. So like 20 degrees versus 70 degrees. So we're just verifying the identities here. Let's look at this one. Is on your notes? Yeah. Okay. So expanding the difference sine formula. It's sine, cosine, same sign, plus sine, cosine, cosine, sine. In that order. We're trying to verify that it equals sine of x. So a trig proof, if you will. Well, the sine at pi is 1. So this guy is a 1. And then the cosine at pi is a 0. Oh, no. Sine at pi is 0, Abuso. Try again. Cosine at pi is negative 1. So what we have here, 0 times anything is nothing, minus negative 1 times sine is a plus sine. Well, ladies and gentlemen, 0 plus sine is sine. Check, verified. Alright, so here we're verifying that sine of 270 plus theta is negative cosine theta. Okay. So, expanding sine of a plus b, that would be sine cosine plus cosine sine. Alright, let's see. See if it checks out. Sine of 270. See if I can do it right this time. That's a negative 1. Cosine at 270 is a 0. So this is negative 1 times cosine plus nothing, which is negative cosine. Alright, verified. Check and check. Alright, now this is different. The directions say find the solution. So sometimes kids get really excited about verifying because they just want to like stop. So this time we're not verifying, we're actually solving. So take a deep breath on this one, guys. This is a little involved. This is on your notes. Go down to number 11 if you could. So, cosine pi over 4 minus x. I'm going to expand this into our cosine difference formula. So cosine plus sine, and then there's a big subtraction sign, and I'm going to use parentheses on this next part because I have to distribute that subtraction in a moment. So this guy, this was this expanded. Okay. So now this red part is sine, cosine, same sign, sine, cosine, cosine, sine. Alright. The gross. If you don't mind, I'm going to go ahead and distribute this subtraction here, and then if I throw it in here, this becomes a plus, because I'm really kind of over thinking about what these terms are. Alright, cosine at pi over 4 is square root of 2 over 2, still times the cosine of x, plus sine at pi over 4, also square root of 2 over 2, times the sine of x, and then this is a minus square root of 2 over 2 times the cosine of x, and then this becomes, we said, a plus sign, square root of 2 over 2 times the sine of x. I feel like we have some canceling terms here. Let's check it out. Alright, so right here, boom, these guys are gone, and then we add 2 of these together. These are like terms, so you have 2 square roots of 2, think about that, over 2. I think you just have square root of 2. So we have square root of 2 times sine x equals negative 1. And then trying to solve this baby. There's probably an easier way to get through this work, but here I am, solving away. So you have sine of x equals, if I rationalize this, negative square root of 2 over 2. And they want all solutions between 0 and 2 pi. Thank goodness, my favorite kind of question. So that would be 5 pi over 4 and 7 pi over 4, right, for a negative sign value. Yeah. Alright, nailed it. Whew. That was fun and exciting. Alright, number 12. Alright, I got time for this. Alright, sorry, I got a class coming in a minute. This is kind of strange. If you notice right off the top of the problem here, we have 2 of the same thing. So how about I rewrite that as 2 times this, because I have two of them. So instead of rewriting sine of pi plus x, I'm just going to expand it right here, because I have two of them. So sine pi plus x would be sine cosine plus sine cosine cosine sine. Maybe during class I'll chant this for you, huh? Alright, let's talk about what we got here, guys. Sine of pi is 0. So this whole term's gone. Cosine at pi is -1. So you have 2 times -1 times sine. So you have -2 sine x equals 1. And then solving for sine, I want to know where your sine is -1/2 on one rotation of the unit circle. So that would be the square root of 6 families with the -1. So that would be 7 pi over 6, right? Yeah, and 11 pi over 6. Awesome. Alright, let's see. I'm trying to look ahead to see who's the most fun. I mean, they're all like equally fun, right? The next one's tangent. It's just, there's a fraction in the tangent one, which doesn't make it any more difficult or not. I'm not worried about it. Let's do number 14 though, because these are the most typical ones you'll see. Now, bad news, these are not the same term, so I can't combine them like I did on number 12 or whatever that was. So I do have to kind of expand them separately. So let's start with this guy. So sine, cosine, sine, cosine, cosine, sine, plus, at least I don't have to distribute a negative anymore, and then sine again. So sine, cosine, minus sine, cosine, cosine, sine. And remember, we're solving, so we're not doing identity work anymore. Okay, cosine at pi over 3 is 1/2. So that's a 1/2. Sine at pi over 3, however, is square root of 3 over 2. So this dude is, oh, you know what? I think I'm doing too much work here. Isn't this term going to cancel with this term? So anywho, what we have here is a half sine plus another half sine, so we have like a whole sine. So I have sine of x equals 1. Oh man, that was actually a really easy question. When is sine 1? That would be at pi over 2 only. Alright. Great news, we can go back. I can do number 13 with you. Alright, so we have the tangent, and this is another case where there's two of them, if you notice, tan plus tan of the same thing. So you have 2 times the tangent of pi minus x. So if I use my tangent subtraction or difference formula, that becomes tangent of a, which is pi, minus, is it minus tan? I always forget this one. Minus tan x over 1 plus tan pi times tan x. I never remember that one, so I apologize for me having to sneak a little peek at my notes. Alright, so tangent at pi, sine over cosine, that's 0, isn't it? So this is a 0, and this is a 0. So this term's gone, and that's just that. How boring. Alright, so we have -2 times the tangent over 1. I think we just have -2 tangent equals -2. Guys, this is a really easy question all of a sudden. I want to know when tangent's 1. Well, 2 places. Pi over 4, of course, and then the other place where tangent's positive is quadrant 3, so that would be the 5 pi over 4. Did I get them all? Yeah. Alright. So these shouldn't be too terrible for you, and you know, like, I'm not going to say I've taught this recently, but like literally, like, oh gosh, how many years ago? I don't know, the last time I've had to, I taught trig like 5 years ago, but like literally back in high school, long time ago for me. I remember my teacher making me memorize sine, cosine, cosine, sine, cosine, cosine, sine, sine. So it's possible to memorize these, and obviously it's a lot easier to come up with the trades and the manipulations if you have them memorized. You don't have to keep looking back at your pink formula sheet. But, you know, be impressed with my memorization of useless facts, like the difference in sum formulas. All right, good luck.